Welcome back, everyone. Today we are diving into one of the most elegant solutions in modern engineering, post-tension slabs. For decades we've seen the marriage between concrete and steel as a passive one. In standard reinforced concrete, the steel just sits there, waiting for the concrete to crack before it starts working. It's like a safety net that only catches you after you fall. But what if the steel was proactive? In post-tensioning, we transform this relationship into an active partnership. We stretch the steel before the loads even arrived, turning a heavy, brittle material into a resilient, high-performance system. It is the difference between carrying a stack of loose books and squeezing them together so tightly they act like a single solid beam. Why do we go through the trouble of tensioning cables? Because it grants our structures three incredible superpowers. First, long spans. We can create massive open spaces without cluttering them with columns. Second, it acts as a rigid raft for bad soil. If the ground is soft, a post-tension foundation squeezes the entire building together, allowing it to float like a solid boat rather than cracking under uneven settlement. And third, crack control. By keeping the concrete in a permanent state of compression, we effectively close the doors on moisture and corrosion. It's like wearing a tight corset that keeps everything aligned and protected against the elements. The real secret lies in the shape of the cables, or what we call the tendon profile, parabolic draping. We don't just pull the cables in a straight line. We drape them in a curve, low at the center of the span where the sagging is worst, and high over the columns. This creates an upward force that literally fights gravity. Imagine you're holding a heavy skipping rope and someone pulls both ends tightly. The middle of the rope lifts up. This is the load balancing concept. We are using the internal tension of the steel to lift the weight of the concrete and the people on top of it, neutralizing the gravity loads before they even cause trouble. Now, how do we actually build this? There are two main flavors, bonded and unbonded. In an unbonded system, the steel cables are coated in grease and wrapped in a plastic sheath. They stay independent of the concrete forever, like a tendon inside a sleeve. In a bonded system, we place the cables inside corrugated metal ducts. After tensioning, we pump in a high-strength grout to glue the cable to the duct and the surrounding concrete. Think of unbonded as a guitar string that can slide, while bonded is like a muscle fiber fused to the bone. Each has its place depending on the scale and requirements of the project. The magic happens after the concrete has reached about 75% of its strength. We use massive hydraulic jacks to pull the tendons. As the jack pulls the steel, it pushes against the concrete edge, compressing the entire slab. Once the target force is reached, we lock the tendon in place using steel wedges and an anchor head. It's a high-stakes moment. You are essentially preloading the slab with thousands of pounds of force. This internal squeeze is what gives the slab its stiffness and allows it to remain incredibly thin compared to traditional slabs. We're talking about saving up to 20 or 30% in concrete volume. But with great power comes great responsibility. Because PT slabs are so thin, they face a dangerous enemy: punching shear. Imagine a heavy person wearing high heels standing on a thin sheet of cardboard. The heel might just punch right through. In engineering, the column can punch through the slab if the connection isn't reinforced properly. Since we don't have thick beams to distribute the load, all that force is concentrated. We have to use specialized shear reinforcement or stud rails to reinforce these zones. If we fail here, the collapse can be sudden and catastrophic, as the slab slides down the column like a ring falling down a finger. Beyond punching shear, we also have to worry about corrosion and accidental damage. If a single tendon in an unbonded system is cut, say by a plumber drilling a hole in the wrong place, the entire cable can snap back like a broken rubber band, losing its tension across the whole length of the building. This is why as-built drawings are sacred in PT buildings. You never ever drill into a PT slab without scanning it first. We also watch for honeycombing near the anchors where the concrete doesn't settle perfectly. If the concrete crushes at the anchor, the whole squeeze is lost, and the slab loses its superpower. When we get it right, the results are stunning. We can achieve slabs that are 200 mm thick, spanning 10 meters or more. This reduces the total height of a skyscraper, allowing developers to squeeze in extra floors within the same height limit. It reduces the total weight of the building, which means smaller columns and smaller foundations. It's a cascading effect of efficiency. By using steel actively, We aren't just reinforcing concrete. We are optimizing the very physics of how a building stands. It is the ultimate example of doing more with less. In this first part, we've covered the why and the how of post-tension slabs, from the parabolic magic of tendons to the dangers of punching shear. But how do we actually calculate these forces? How do we design the anchorage zones to prevent bursting? In part 2, we will roll up our sleeves and look at the math and the detailed construction sequence. Until then, keep looking up at those long spans and remember, it's the invisible tension that's doing the heavy lifting. Let's discuss it in the comments. If you found this breakdown helpful, hit the like button and subscribe to join our engineering community. See you in the next lesson at Strong Foundation Engineering.